Hello students, welcome to Physics World by Sudhakar. The topic which I am going to discuss today is the most important topic from all exams point of view. From GATE Physics to CSIR to JNU exam or BHU exam or HU exam, right? You will find these topics. Okay, the questions keep on coming very frequently. Okay, right? So don't try to miss out this video. Okay, watch it till the end. What are those topics? It's known as first energy equation and second energy equation. In the earliest videos in thermodynamics, okay, I have said that for an ideal gas, internal energy is purely a function of temperature, okay, such that it does not vary with either pressure or volume. If you keep temperature constant, that is dou U by dou V at constant T equal to dou U by dou P at constant T equal to 0, we said internal energy changes only with temperature. Okay, because in an ideal gas there are no intermolecular attraction forces. Ideal gas internal energy depends only on temperature. Now we are going to see that mathematically. Okay, and how internal energy of a real gas or van der Waals gas varies with volume and varies with pressure. Okay, the variation of internal energy of a real gas with volume is known as first energy equation, and variation of internal energy with pressure is known as second energy equation for a real gas or van der Waals gas. Okay, before going into the energy equations, right, I'll discuss what is known as Ts diagram or Tephigrams. Okay, here temperature T is taken on the x-axis. Temperature T is taken on the x-axis. Temperature T is taken on the y-axis and entropy is taken on the x-axis. Okay, this is known as Tephigram or Ts diagram. Now, how to draw a Ts diagram is, first we will see a PV diagram of a Carnot cycle. Okay, indicator diagram or PV diagram. We have got a Carnot cycle to be like this. Okay, which involves 4 steps here. Which involves 4 steps. A to B is first step. Okay, B to C, C to D, and D to A. What is A to B? It is reversible isothermal expansion from P1 V1 to P2 V2 at a constant temperature T1. Okay, the system absorbs Q1 amount of heat from the source at high temperature T1. So, increase in entropy, what you call, so Q1 amount of heat is absorbed. So, what is increase in entropy system? Q1 by T1. B2C is a reversible adiabatic process. In a reversible adiabatic process, delta Q equal to 0, change in entropy is equal to 0. Okay, but system's temperature falls down from T1 to T2. Okay, third step, C to D, is a reversible isothermal compression from P3 V3 to P4 V4 at a constant temperature T2. The system rejects Q2 amount of heat into the sink at lower temperature. Okay, right? And D to A is again reversible adiabatic process in which the entropy of the system remains constant, but temperature increases from T1 to T2. Okay, now how do we represent this on the Tephigram or Ts diagram? We see initially, right, suppose that this is a high temperature T1 is here, okay, low temperature T2 is here. Now we consider some point as initial point of entropy, right? At a constant temperature T1, system is absorbing Q1 amount of heat. System is absorbing Q1 amount of heat. So what will happen to the entropy of the system? Entropy of the system increases by Q1 by T1. Okay. So entropy keeps on increasing. Temperature remains constant, means we will get a horizontal line. Okay. From an initial point A till a final point B, right? Increase in entropy of the system is Q1 by T1. Okay, the second step, B to C, is a reversible adiabatic process in which entropy remains constant but temperature falls down from T1 to T2. Okay, so temperature is falling down from T1 to T2 means at a constant entropy, we'll get a vertical line like this. Entropy should be constant. Temperature should decrease from T1 to T2 means it comes like this up to the point C. Okay, now the third step is reversible isothermal compression, where system at a constant temperature T2, system loses energy into the sink. Okay, so entropy of the system keeps on decreasing by what amount? Q2 by T2. Okay, so entropy, temperature remains constant means we'll get a horizontal line. Entropy is decreasing means I have to go to left like this. Okay, up to what point I should go like this? Entropy decreases by Q2 by T2. In a reversible Carnot cycle, Q1 by T1 is equal to Q2 by T2. So whatever is the increase in entropy from A to B will be the decrease in entropy from C to D. Okay, like this. Okay, the fourth step is reversible adiabatic compression from D to A. Okay, in a reversible adiabatic compression from D to A, entropy remains constant, temperature increases from T2 to T1. Okay, so temperature increase from T to T1 means it will be like this. it will be like this. Okay, right? So this is the Carnot cycle represented on a TS diagram. Okay, what is the shape of the curve we got? Okay, it is a rectangle. So Carnot cycle in TS diagram is a rectangle. Okay, in a rectangle, what is the area enclosed by the Carnot cycle in TS diagram? I want this area. What does that area represent? In a PV diagram, okay, area enclosed by the Carnot cycle gives you net work done. In any indicator diagram or in any PV diagram, okay, for a cyclic process we get closed loop. Area enclosed by the closed loop is nothing but the net work done in that process. Similarly, what is the area enclosed by the closed loop in TS diagram of Carnot cycle we see now. Okay, this area A, B, C, D area is nothing but area of, I'll call these points as A, E and F. Area of the rectangle A, B, F, E minus area of the rectangle D, C, F, E. Means from this area, if I remove this area, I'll get the area enclosed by the Carnot cycle in TS diagram. Now, what is this area? Nothing but T1 into Q1 by T1. Okay, length into breadth. This length is nothing but T1 into this breadth is Q1 by T1. So Q1 by T1, okay, is nothing but Q1. Okay, so what is the area under this curve AB, right? It gives you the amount of heat extracted from the source. Okay, that is Q1. Now, what is this area? This area is nothing but CD into this diagram DE. Okay, that is nothing but T2 into this length is T2. Okay, width is Q2 by T2. Q2 by T2, T2 and T2 get cancelled. So this is Q2. What is Q2? Heat rejected into the sink. Means the heat engine is taking some Q1 amount of heat. Q2 amount of heat is getting rejected into the sink. Whatever is Q1 minus Q2, that is nothing but the area enclosed by the Carnot cycle in TS diagram. Okay. So what is Q1 minus Q2? We call it as energy which got converted into useful work. That is known as available energy. Okay, available, we should not call it as work because it is a TS diagram, right? In a PV diagram, PDV gives you work. In a TS diagram, TDS will give you energy. Okay, so it is available energy. So the area enclosed by a Carnot cycle in PV, in TS diagram gives you available energy. What is available energy? Energy which can be converted into useful work. Okay, next one. Well, how do we write the efficiency of a Carnot cycle? Efficiency of a Carnot cycle, how do we find? The advantage of TS diagram is the moment we look at that area enclosed by a closed circle in TS diagram, we will see how much is energy is available to be converted into work. Means work value of the fuel can be understood very easily. Second one, we can calculate efficiency also. From a PV diagram, we cannot calculate efficiency unless T1 and T2 are specified. But in TS diagram, T1 and T2 are there. Carnot engine's efficiency depends only on, right, T1 and T2. So what is the efficiency of a Carnot cycle? T1 minus T2 by T1. What is T1 minus T2? T1 minus T2, this is T1, AE is T1, okay, minus T2 is nothing but DE by, again T1 is nothing but AE. What is AE minus DE? Nothing but AD, nothing but AD by AE. Okay, this directly gives you efficiency. The advantage of drawing TS diagram is by directly looking at the graph itself, I can understand what is the efficiency of that Carnot cycle. How? This length by this length will give you efficiency. AD is this length. Okay, AE is this length. This length by this total length will give you the efficiency directly. Okay, in some exams, right, you will find questions like there are two Carnot cycles, right, whose TS diagrams are like this. Okay, this is curve 1, curve 2 like this, they will give. Okay, this is T1, T2, this is T1, okay, this is T1, this is T2. Which engine? They'll call this as engine A, engine B. Which engine is more efficient? Okay, there is an engine is working in a cyclic process, right? Like this from P to Q to R. Okay, there are two engines, like which engine's efficiency is more? Okay, this length by, if it's a TS diagram, this length by this length. Okay, this length by this length is nothing but efficiency. If they are equal, we can say eta 1 equal to eta 2 like that. Okay, very easily we can compare efficiencies and we can estimate the work value of the fuel also, means available energy which can be converted into useful work. Okay, this is the significance of TS diagrams, important from exam point of view. Now we'll go into the first energy equation, okay, which is extremely crucial from all entrance points, not only from subject point of view, concept point of view. I can understand how internal energy of a real gas varies with volume. So, okay, from first energy equation, how internal energy varies with the pressure at constant temperature for a real or van der Waals gas, that comes in first energy equation. Okay, now how do we start first energy equation? Okay, first energy equation. I'm repeatedly saying, very, very important from the all India level MSc physics entrances point of view, gate physics point of view, and even from CSIRJRF. Okay, right, first energy equation. From the first law of thermodynamics, we have dq equal to, right, du plus pdv. Okay, second law says that dq equal to Tds. Okay, so wherever dq is there, put Tds here. So Tds is equal to, right, du plus pdv is the equation combining first and second laws of thermodynamics. Okay, from this, change in internal energy du equal to, I can write it as Tds minus pdv. du equal to Tds minus pdv. Okay, now I want to find out the change of internal energy with volume. Okay, so I'll divide it with the dv on both sides. du by dv equal to Tds by dv, dv by dv. dv by dv is nothing but 1. So there's nothing but du by dv equal to, okay, t into ds by dv minus p, it will be. Okay, now if I put a restriction that at constant temperature, these differentials will become partial derivatives. Okay, so this equation now becomes what? Okay, dou u by dou v. Dou u by dou v at constant temperature is equal to T into dou s by dou v at constant temperature minus P. Now use Maxwell's equation. Convert this dou s by dou v at constant T using Maxwell's equation. Okay, what do you do? Dou u by dou v at constant T equal to T into, I told you, don't try to by heart Maxwell's equations. There is an easy way of identifying. If you know LHS, you can easily write RHS. If you know RHS, you can easily write LHS in Maxwell's equations. Okay, what is the technique we have seen in last video? Okay, where whatever is the constant here, that goes into the denominator. Okay, T is constant here, so it goes as denominator. Volume is in the denominator, that becomes constant here. S over SV, T are over, only thing left out is dou P, pressure. Okay, since P by T term is there, the equation is positive only. So you can convert this using Maxwell's equation, dou S by dou V at constant T equal to dou P by dou T at constant V minus P. This equation, okay, is known as the first energy equation. This equation is known as the first energy equation. Okay, right? What is its significance? I can find out how internal energy of gases vary with what you call volume when temperature is constant. Okay, now example is what happens for an ideal gas. Ideal gas we have already seen in the beginning only, that dou u by dou v at constant is equal to 0. Now I'm going to derive that mathematically using Maxwell's equations and this first energy equation. Okay, right? Now according for an ideal gas, okay, we have PV equal to RT. Okay, PV equal to RT. So what is dou P by dou T at constant V? Dou P by dou T at constant volume. Dou P by dou T at constant volume is nothing but, volume is constant, no, bring it to the RHS, it becomes R by V. So dou P by dou T at constant V for an ideal gas is R by V. Substitute that in this equation, right? So RHS becomes T into R by V minus P. Is nothing but RT. RT is again PV only. Okay, PV by V minus P, V and V that gets cancelled, P minus P is equal to 0. So for an ideal gas, dou U by dou V at constant T is equal to 0. Okay, what we have, what you call understood from van der Waals equations point of, van der Waals forces point of view is getting derived mathematically here. The most interesting part and the one that is important from exams point of view is for a real or van der Waals gas. Okay, for a real or van der Waals gas, right, what happens to this first energy equation now we have to see. Okay, what is the equation of state for a van der Waals gas? P plus A by V square into V minus B is equal to RT for 1 mole. Okay, right? Now I want to evaluate dou P by dou T at constant V. So pressure term is here. So I'll take this V minus B, R equal to RHS. So P plus A by V square is equal to RT by V minus B, such that P equal to RT by V minus B minus A by V square. So minus A by V square it will be, this is nothing but pressure P equal to, this is nothing but pressure P equal to RT by V minus B minus A by V square. Now find out dou P by dou T at constant V. Dou P by dou T at constant V equal to, differentiate this equation with respect to temperature. So dou P by dou T at constant V, temperature is here, this becomes R by V minus B, A by V square is a constant only. Okay, because at constant volume we are evaluating, this term becomes 0, right? This simply becomes R by V minus B. Substitute this value of dou P by dou T, right, equal to R by V minus B in our first energy equation. Okay, what do we get? Okay, okay, if you substitute dou U by dou V at constant T equal to T into, right, R by V minus B is nothing but RT by V minus B. This is RT by V minus B, right, minus P is there. P is nothing but RT by V minus B minus A by V square. So minus RT by V minus B, right, minus of minus will become plus A by V square. RT by V minus B, RT by V minus B gets cancelled. So dou U by dou V at constant T is equal to A by V square for a real or van der Waals gas. For a van der Waals gas, okay, internal energy, right, varies with temperature at varies with volume at constant temperature. For an ideal gas, if you keep temperature constant, internal energy remains constant even if you increase or decrease the volume. But for a real gas or a van der Waals gas, internal energy varies with volume also even though temperature is constant. So what is dou U by dou V at constant T equal to A by V square? This also may come in the examinations. Remember that for a van der Waals gas, dou U by dou V at constant T equal to how much? Okay, it is A by V square. Now exactly how, what you call internal energy varies with volume, now we will see now. So here I'll take, let internal energy be a function of, it's a function of temperature even for an ideal gas. For a van der Waals gas, let the internal energy be a function of temperature and volume. Internal energy be a function of temperature and volume. So change in energy, internal energy du equal to, how do we write, dou U by dou T at constant volume into dt, okay, plus dou U by dou V at constant temperature into dV. This is how we write. Okay, du, when u is a function of two variables, change in that u equal to du equal to is written like this. Okay, now what is dou U by dou T at constant V? Dou U by dou T at constant V nothing but molar specific at constant volume. Okay, so this is nothing but Cv into dt plus dou U by dou V at constant T into dV. This is our change in internal energy. Okay, now we have evaluated dou U by dou V at constant T, right, earlier. We have evaluated dou U by dou V at constant T equal to A by V square. Now I'll substitute that equation here. Okay, it becomes what? It becomes du, change in energy, du equal to Cv dt plus A by V square into dV. Okay, because dou u by dou v at constant temperature is equal to A by V square. So it is, right, Cv dt plus A by V square into change in volume dV. What is internal energy? Integral du is nothing but u. So internal energy u equal to integral Cv dt plus, okay, integral A by V square dV. Okay, integral 1 by x square is minus 1 by x, isn't it? So integral A by V square dV equal to nothing but minus, okay, minus A by V, minus A by V plus A by V square integral nothing but minus A by V plus some integration constant C. Okay, so this is the expression for internal energy of a van der Waals gas, right? How internal energy changes with volume. In an isothermal process, means when you keep temperature constant, dt is equal to 0, first term vanishes, u equal to minus A by V. That is, for a real gas or a van der Waals gas, as the volume increases, okay, because minus A by V term is there, internal energy increases. So as volume increases, actually A by V means as volume increases, it appears as if internal energy decreases, but it is minus A by V term, isn't it? Therefore, as volume is increasing, internal energy also increasing. So for a van der Waals gas, right, as volume increases, internal energy increases. For an ideal gas, as volume increases, internal energy remains constant at constant temperature. That is the significance of first energy equation. Okay, next we'll go into the second energy equation. Okay, second energy equation gives us variation of internal energy with pressure. Okay, right, now how do we proceed for again du equal to Tds minus Pdv. Now we are going for second energy equation. Okay, second energy equation. du equal to Tds minus Pdv. Second energy equation about variation of internal energy with pressure. So I will divide it with pressure. Okay, dp, change in pressure, du by dp equal to T ds by dp minus P dv by dp. dV by dP. Now I want at a specific condition that temperature should remain constant. So when I put some condition like temperature should be constant, this becomes a partial derivative. Dou u by dou P at constant temperature is equal to T into dou S by dou P at constant temperature minus P into, right, dou V by dou P at constant temperature. Okay, now again use Maxwell's equation. Okay, convert this dou S by dou P at constant T using Maxwell's equations and put that in this equation. So what do we get? Dou u by dou P at constant temperature is equal to T into, now using Maxwell's equations, convert this dou S by dou P at constant T. Use our technique, okay, what we have seen in the last video, right, or just before. So it is nothing but denominator will get dou T, okay, constant will be pressure, S over P over T over, only volume is remaining, so dou V. Okay, there is no S P by T or T by P term is not there here or here, so it should be minus sign. So minus T dou V by dou T at constant P minus P dou V by, dou V by dou P at constant T. This is our second energy equation. Second energy equation describes the variation of internal energy with temperature, with pressure at constant temperature. Okay, right, for an ideal gas, for van der Waals gas, you can find out, evaluate that what you call dou V by dou T, dou V by dou P, substitute in this equation, you'll get dou U by dou P. For an ideal gas, we know that dou u by dou P at constant temperature must be equal to 0. I'll just check whether it is coming or not. We'll see. Okay, right, now for an ideal gas, we have PV equal to RT dou V by dou T at constant P. Dou V by dou T at constant P is nothing but R by P. So dou V by dou T at constant P is equal to R by P. Substitute R by P in this equation. So what do we get here? Okay, it is minus T into R by P minus P into dou V by dou P at constant T. This in the numerator we have RT. RT equal to PV, according RT equal to PV. So P by P will get cancelled. What remains here is minus V will remain. Minus P into dou V by dou P at constant T. Okay, now I have to see, right, what is dou V by dou P at constant T for an ideal gas. Okay, so how to get dou V by dou P means differentiate this equation. It is P dV plus V dP is equal to R dt. R dt. Okay, in an isothermal process, dt equal to 0. So P dV is equal to minus V dP. What is dou V by dou P at constant T, right? P into dou V by dou P at constant T is equal to minus V, we get. So in this expression, right, dou U by dou P, dou U by dou P at constant T is equal to minus V minus P dou V by dou P at constant T. We got P dou V by dou P at constant T is minus V. So nothing but minus V minus of minus V. Minus of minus V, that is minus V plus V is equal to 0. Okay, so for an ideal gas, dou U by dou P at constant T is equal to 0. Dou U from second energy equation. From first energy equation, dou U by dou V at constant T is equal to 0. Okay, for van der Waals gases, how they vary, we have seen. Okay, significance of first and second energy equations, they are important from physics concept point of view and from examination point of view also. In the next video, we will discuss what are known as TDS equations. Okay, there are 3 TDS equations from Maxwell's equations which can be obtained easily. Those TDS equations are very useful in calculating what is the amount of heat required in compressing a liquid, right, at constant temperature, right? When I compress the liquid, how much heat should be transferred, okay? Or when I am compressing a gas, okay, van der Waals gas, real gas or ideal gas at constant temperature, what is the amount of heat that should be transferred, what is the amount of work that should be done, etc., can be understood very easily from those TDS equations. Okay, that we'll cover up in the next video. Okay, and just before ending, I'll just give you one problem, okay, which has appeared in the previous examinations. A good problem. Okay, I found it interesting. Okay, right, this is the problem actually. Okay, now look at this. The relation between pressure and volume of an ideal gas in a reversible process is given as P equal to AV plus B. P equal to AV plus B means relation between pressure and volume is given, where the constant A is minus 31 by 56 Pascal per meter cube and the constant B is 255 by 7 Pascals. The volume at which temperature attains maximum is, the volume at which temperature becomes maximum is asking. Okay, here no temperature is given, no volume variation is given. He has simply given one relation, that too is what type of process also he did not tell. He simply said reversible process. We don't know whether it's isothermal, isobaric, isochoric or anything. Okay, in a reversible process, the variation between pressure and volume is given as P equal to AV plus B. Only one more hint what he has given is it is an ideal gas. It is an ideal gas. So the volume at which temperature becomes maximum, at what volume? The options given are 32.9 meter cube, 329.7 meter cube, like that. 4 options have been given. Okay, now take this as an assignment. Okay, try to solve this on your own, right? I'll give you the solution in our next video, right? I'll stop here for today. Thank you.